Okay, everyone, this is my first screencast of Phi, and we're going to talk about titration. So here are the notes. They're also on Canvas, and I'm going to go through and explain what you did for your lab and how to do the calculations. So with titration, you're either adding an acid to a base or a base to an acid. And the one you'll know the concentration of, and the other one you're finding the concentration of. When you get to the equivalence point, that's when the moles of H3O plus equals the moles of OH minus. And again, H3O plus and H plus are the same thing. I'll usually just say H plus because H plus only exists in water. So that's the equivalence point that we're looking for with titration. This is a titration curve. So with the one that we did in lab, you will have HCl solution to start with. That's the one you don't know the concentration of, and you're adding NaOH to it. So at the beginning, the pH will be at about 1 or whatever, it'll be low pH. You're only having acid in there. And you're going to start adding base. Well, you'll have a lot more acid in there as you're just adding base by drop or by milliliter. So the pH will slowly start to raise as you're adding more and more NaOH until you've added almost as much NaOH as you had HCl in there. Then all of a sudden, it'll shoot up in pH with just a drop or two because now you've added as much NaOH as HCl. So you've neutralized all of that, and you've also, it's pretty impossible to add just exactly the amount of NaOH as HCl you have in there. So even in just a drop, there's so many ions that you're all of a sudden going to have more base in there than you have acid. So the pH shoots up, and then as you continue to add NaOH, now the pH is barely going to go up because you're already at a base. So with this strong acid, strong base, you'll get this big jump when you're close to the equivalence point, and right smack in the middle of it at pH 7, that is the equivalence point. That's when you've added exactly as much OH minus as you have H plus. So for strong acid, strong base, you get the big jump in the curve, and the equivalence point is at 7. The pH curve, titration curve for a weak acid with a strong base or a weak base with a strong acid won't exactly look like this. So strong acid, strong base, big jump, and the pH at the equivalence point is exactly 7. We're going to use an acid-base indicator, or you did if you already did the lab, an acid-base indicator that changes color at different pH. The one we used, phenolphthalein, is colorless in acid and turns pink at about a pH of 8. The endpoint is when it turns color, and we're choosing an indicator that's close to the equivalence point on when it changes color. So again, in that big jump, there's only maybe a drop, and you're going to go from a pH that's acidic all the way up to pH that's basic. So it'll just one drop, as many of you noticed, will make it change pink. And that's when you're at the end point, but again, we are going to equate that to the equivalence point. So your task with the lab was to find the exact concentration of a solution of NaOH that you made by using a known amount of acid. The acid that we used is called potassium hydrogen phthalate, abbreviated KHP. So with the titration, we knew the amount of KHP we were adding. You dissolve that up as a solid. You could weigh out an exact amount. And then you were adding the NaOH until you got to the end point. Then you could, by calculation, figure out what the exact molarity of the NaOH was. You knew it was around 0.1, but it wasn't exactly 0.1. And then once we know the exact molarity of the NaOH, you'll then be able to find the concentration of an unknown HCl. Again, the KHP is called potassium hydrogen phthalate. It is not a potassium with a hydrogen with a phosphorus. KHP is the abbreviation for it. The molar mass of it is 204.2. It's a solid. You can weigh out an exact amount of it, and when it's titrated, it acts like a strong acid in that all of the H+, the acidic hydrogen, will be neutralized by the base. So at the equivalence point, the moles of the KHP will equal the moles of the H+. Okay, so that's key. That's why it's a strong acid, is acting like a strong acid. All of the H comes off and gets neutralized by the OH minus. So you can find the moles of your KHP by dividing the grams you used, and everybody used a different amount. It was like 0.4 something, 0.3 something, whatever. Divide that by the molar mass of the KHP, which is 204.2, and that's going to give you your moles of KHP, which then is equal to your moles of H+. Okay, and then now that you know that amount, you can use that to say, okay, your moles of KHP equals your moles of H+, that equals your moles of OH minus at the equivalence point. And then since there's one OH in NaOH, that also equals your moles of NaOH. So now to find the molarity of the NaOH, you'll just take those moles, divide by the liters of NaOH that you added from the burette, and that's going to give you your molarity. Make sure you put your volume in liters, not in milliliters that you wrote down. Okay, it has to be in liters. Now, once you know the molarity of your NaOH, and if you did more than one trial, you could average those unless you knew that one trial was a lot better than the other, then you use the better trial. So you'll have the molarity of your NaOH, and then you'll use that to find the molarity of another solution, an HCl solution that you don't know the concentration of. So I'm going to do an example problem using the NaOH to find the molarity of the HCl. It's really just what you had done to find the molarity of the NaOH. Okay, so these won't be the same values as yours, but you'll plug in your own numbers. So let's say you got a 25 milliliter solution of HCl neutralized by adding 18 mils of 1 molar NaOH. And if you know the other was our indicator. So it took 18 mils of 1 molar NaOH to neutralize at 25 milliliters. What's the concentration of the HCl? So to find moles of NaOH used, liters times molarity is moles. That's going to give you your moles of NaOH. Then you will have your moles of OH minus because they're equal. And then you also know that that's your moles of H plus at the equivalence point. And so now we have our moles of OH minus, and then also knowing that HCl has 1 H plus, that is our moles of HCl also. So now to find the molarity of your HCl, you're just dividing the moles of HCl by the volume of HCl, which was 25 milliliters or 0.025 liters, and we found the molarity of our HCl. So that's exactly what you're doing in your lab. Since the HCl had 1 H plus and the NaOH just had 1 OH minus, there is a shortcut where you can find the molarity of one from the molarity of the other. And that's just MAVA equals MBVB. Molarity of acid times volume of acid equals molarity of base times volume of base. Plugging in the volume of the acid, 0.025 liters, plugging in the molarity of the base that I had already found, and then plugging in the volume of base in liters, I can solve for the molarity of the acid. So that's a little shortcut, same result but doing it just a little bit faster. But you cannot do that if your acid has more than one H, because then that's not true that the moles of H equals your moles of acid. Or if your base has more than one OH minus, it's not true that your moles of base equals your moles of OH minus. So for instance, if you were using H2SO4 for your acid with some base like NaOH, or if you're using some base that had two OH in it, H's in it like BaOH2 as your base with some acid like HCl, then you can't use that shortcut MAVA equals MBVB, because it will not be true. Okay, so you can't use it if your acid has more than one H or your base has more than one OH. So I'm going to show you lastly one problem like that, because there's one on the lab that has you doing a neutralization with either your base has two OHs or your acid has two H's. So in this case, 25 milliliters of H2SO4 was neutralized by adding 18 mils of 1 molar NaOH. And so same beginning, the NaOH we used was 1 molar, and we used 18 milliliters of it. So that gives us moles of NaOH, which is moles of OH minus because it's a 1-to-1 ratio of OH to OH. But now it's a little bit different from the other one because the moles of OH minus does equal the moles of H plus, but our acid, there's 2 moles of H plus for every 1 mole of H2SO4. Even though the second H is not a strong acid, when you're titrating, both H's would get titrated. Okay, so when you're doing this calculation, you have to count both H's from the H2SO4 to get neutralized. So that's where the difference is, that it's a 2-to-1 ratio to go from moles of H plus to moles of H2SO4. Okay, so then now that cuts down in half the moles of H2SO4. So it's different. It's not the same as the moles of NaOH. Okay, it got cut down. So then lastly, now that we have our moles of H2SO4, you still divide by the liters and you get the molarity of the H2SO4. Okay, so again, all these notes are written out for you. And so I hope you can finish your labs. And we will stop there for today.